Okay. Hello, everyone. My name is John Ryan. I'm a senior here at NYU. I'm majoring in math and computer science. And today I'm going to be talking to you about the game of Conway Soldiers. Before I start, I just want to say I put my name on the board, so feel free to shout at me and tell me to stop if I'm going too fast at any point. I've allocated time such that I should only spend like 50 minutes talking. So if you have questions, there's definitely time for that, so feel free to stop me. And I wrote my email on the board just in case you have any questions about this talk, or want more resources or further suggested reading, or in case you have any questions about college or majoring in math in general, or computer science, or physics. So today I've written two formula on the board that I'm going to use very extensively, so I first want to just make sure we're on board with these formula. The first is just a standard geometric series. If we take some number and sum up every positive power of that number, we will get this closed form answer. So for example, 2 plus 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 up until, I'm going to use 0.2. Up until infinity will equal 1 over 1 minus 0.2. So that's what this formula will be used for. I'm not going to suddenly use it without saying that I'm using it, so I'm just putting it right there for your reference. This is a statement we're going to accept to be true. So today we're going to talk about Conway Soldiers, as I said. Can I see a show of hands? Who has heard of this game before? No one has heard of Conway Soldiers. Perfect. Well, I guess just a smidgen of background. This is probably one of John Conway is a famous mathematician, still alive today. I think he contributes to Numberphile a bit, anyone who watches that. This is probably one of his more famous works, not necessarily that it was a resounding contribution to the progress of mathematics, but in that it's one of the most beautiful proofs that can be demonstrated, in my opinion, but also it is a famous proof for the very reason that it doesn't require very much knowledge to understand the proof. And yet it's quite beautiful. It uses concepts like energy and the golden ratio and applies to a checkerboard game. So, and has anyone ever heard of the book or the play, The Curious Incident of the Dog in the Nighttime? Yeah, so this is referenced in that book as well, and that's how I came to know about it, is that the autistic main character likes to play this game in his head with the infinite checkerboard somehow contained within his memory. I mean, not all of it, but most, a good amount of it. So first, I want to talk about, the game. So the game is played thusly. I have an infinite checkerboard. I've only written a bit of it right here. And there's a horizon which separates the north and the south path. When we play, we play by starting with an initial configuration of soldiers, all of which must be placed in cells below the horizon. So an example of an initial configuration would be if I put where the red circle indicates a soldier. So the goal of Conway Soldiers is to end the game with a soldier as high above the horizon as possible. The first question is, how do the soldiers move? Well, the rule of the game is very simple. To move a soldier, let's say I want to move this soldier, I simply have him jump over this soldier and land here. So this soldier gets deleted in a jump, and he jumps, so he's gone, or she. Just another example, I'm going to move this soldier to this square by having that soldier jump over this square. Red is bad choice. Everyone understand? Any questions about that? Okay, good. Let's make this a bit difficult. So I'm going to ask sort of an easy question up front. I've written a table here. So I want to know what's the minimum number of pieces necessary in an initial configuration to end with a soldier on the first level. So for example, in this case, I started with 4 soldiers in my initial configuration, and I'm not even done yet, and I've already achieved that 1 soldier is on level 1. So So who can tell me what's the minimum number of soldiers necessary to get to level 1? Yeah.
2.
2, yeah. So that's very initial. That's a very simple initial configuration. You just draw like this. Okay? All good so far. Okay. So what is the minimum number to get to level 2? Yeah. 3. How do I do it?
Bottom one jumps over.
Uh-huh. And I have a third one there somewhere. Well, you do have that, but in fact, it takes, yeah.
Is it 4?
It's 4.
Yeah.
Yeah. Because if I start like this, okay, really I'm going to switch to white before it's too late. If I start like this, then I can advance this one up here by performing a vertical jump. I can advance this one here by performing a horizontal jump. And I can advance this one here by performing a vertical jump. Now I started with 4, and I am up to, well, I have 1 left, but I'm up to level 2. Feel free to read this, like, I mean, I wasn't about to pass around a grid because I didn't want to spend so much paper on that, but yeah, definitely feel free to play with this, just to strengthen your understanding. So as for the 3rd level, I'm going to spare you the risk of guessing, and I'll just tell you that the answer is 8. And I'll demonstrate it right now. Okay, so if I have this initial configuration, I perform a vertical jump here, a horizontal jump here, a vertical jump again here. Wait, am I doing this right? Yeah. Another vertical jump here, a horizontal jump here, a vertical jump here, and then another. Yeah, so, yeah, I got there. 8 is the answer. For those of you who weren't watching, I did it, I promise. So anyway, so just to fill in this table, we've got 2 was the first one, that's pretty trivial. 4 is the next one, 8 is the third one. Who can tell me what the next one is? No, it's 20. So yeah, so we have sort of a sense of a pattern that's growing faster than exponential. It's not doubling every time. So does anyone know what they think the number might be for the 5th level? No, I'm really testing whether you've heard this one before. I mean, is it going to jump to 10,000 or what? The answer is that there's no number. You can't physically get to the 5th level. It's mathematically impossible. So a big attractive factor about this problem and this proof is that that statement is almost sort of bewildering. It's like, what? Just give me like an hour and a pen and paper, I'll get there for you. Like there must be some way we have the technology, we have computers, we can get to the 5th level, but in fact, it's impossible. With any initial finite configuration of soldiers, you can't get to the 5th level. And so what this talk will be is a proof of that fact. Okay? And good. Okay. So, any questions? Okay, so the first thing we're going to talk about in this proof, I mean, beginning proof, this is the proof, is the energy. So, don't fear if you haven't taken physics or whatever energy would come up in. This is going to be a definition-based concept. I'm going to define for you what the energy of each cell is, and I'm going to define for you what the total energy is. Before I start going down this road, I'd like to give a brief proof sketch, demonstrating what exactly am I going to do that will prove this. So here's the idea. First, we're going to define energy so that target cell has energy 1. Okay? Yes. So that's step 1. Step 2 is prove no soldier jump increases So I'll explain this in just a second, but let me just write the third thing. Show any initial configuration has total energy less than 1. So this might sound a bit scary at first, but it's actually a pretty approachable task. We're going to give every cell an energy. So for example, I could give, for example, I'm not going to do this, but for example, every cell could have the energy, which is the number of the row. So this cell would have energy 1, this cell would have energy 1, this cell would have energy 2, this would have energy 3, etc. Then we're going to say that the total energy of the board at a given point is the sum of the energy cells, which have soldiers on them. So just to demonstrate this concept, why don't I draw 2 soldiers in this board and ask, what is the total energy of this board? Yeah, 3. Yeah, 3, exactly. I have a soldier on a cell with energy level 2 and a soldier on an energy level cell where it's 1. So 2 plus 1 is 3. If I had another soldier here, the total energy would be 5. Okay. Just making sure. So once I've come up with that definition, then any initial configuration, like any placement of soldiers in the bottom half, like if I ask you to play this game and you say, okay, I'm going to start with this board where I place the soldier here, 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 here. I'm going to start with this. That board has a total energy. Okay? So that's how we're going to use energy. The definition will be such that any cell up here will have energy level 1. So if I had a soldier right here, and this was the board, that was it, there were no other soldiers, I had one soldier right here, the total energy would be 1. Okay? Any questions? Okay. Am I going too fast, too slow? Feel free to let me know.
You said that the soldiers can reach a level of 5.
That's right.
Okay, understand.
Yeah. Yeah, so that is the idea. We're going to say that if a soldier were on this level, it would have energy 1.
5.
But any initial board, like any initial placement of soldiers in this bottom half, will have total energy less than 1. So that's how this proof will proceed. So if any soldier, any initial configuration will have total energy less than 1. And any soldier up here would have energy level 1. Thus, it's impossible to get a soldier up there. Because any jump of a soldier cannot increase the total energy of the board. So maybe this will become a bit less abstract as I go through the details. So, I'm great on time. So the first thing I'm going to do is define this energy. Okay? So, first of all, I'm going to assume that we're only aiming for one goal square. Because if I can get to that square, then in theory, I could start in a different way to get to any square in the 5th row. Like if I had some strategy that could get me to this square, then to get me to this square, I just have to start with the soldiers placed one to the left. Okay. So now I'm going to define this energy based on something that's called the Manhattan metric, or the Manhattan distance, which is sort of thin because, I mean, yeah, which is good. Because I learned about this in Alabama, so the Manhattan metric didn't make sense. So the idea is we're going to give every square an energy that depends on its distance from the goal square in terms of city blocks, in terms of Manhattan distance, which is to say this is 0 blocks from the goal configuration. It is the goal cell. It is the goal cell. This is 1 block away from it. This is 2 blocks away from it. This is 2 blocks away from it. Okay? Any questions? So, right, so here's what I'm going to do. I'm going to say that this block has a to the 0 energy. And I'll say what a is in just a second. But for right now, I'm just going to fill the board in exactly the way that I told you. Every block will have an energy level, which is related exactly to its Manhattan distance, or its number of blocks that you would need to walk to get to the goal square. Okay? So I've just written what the energy levels of each cell are. So we have a to the 0, a to the 1, a to the 2, a to the 3, a to the 4, etc. A to the 1, a to the 2, a to the 3, a to the 4, a to the 5, etc. Any questions so far? Okay, good. So this is the energy level of each cell. Now, right now, I'm going to say what A is. When John Conway did this proof, he started it in exactly the same fashion where he left the A mysterious. He hadn't decided what it was, but he knew that he wanted the proof to look like this, where you'd have a total energy level below the horizon and the energy level of a target block and show that you could never get there. But he needed an A to satisfy a certain property, namely the property that when you sum up a geometric series, like if I were to take the sum of every A in this row, now you're starting to see where the geometric series might come in this block, that it would give me a desirable property. That when I sum up everything below the horizon, I'll get something less than 1. And it turns out that the perfect candidate for this A, which we're not going to be so mysterious as Conway, we're going to say it right out front. We're not going to try to figure out what it should be. The perfect A for this would be an A such that 1 minus A is equal to A squared. So this is a quadratic equation. So if I solve, and I use the quadratic formula, just for my benefit, how many of you have heard of the quadratic formula? Okay, cool. So the solution is the golden ratio and the golden ratio minus 1. So that is sort of the distinguishing surprise of Conway's proof, and for what reason he got so much attention for it, is that the A that we're going to use is the golden ratio. Now, just to reiterate, Conway didn't choose the golden ratio when he started this proof. He looked at how he wanted to prove it, and then he derived the number that would finish the proof for him. He basically made the proof without knowing what A was, and then picked a suitable A such that it worked out. And the only suitable A is the golden ratio. Okay? Now, to be precise, it's actually the golden ratio minus 1, because we're going to take the sum of a geometric series, and we need it to be less than 1. But the point is that it is the solution of the quadratic equation which defines the golden ratio. So that's it. That's the energy level of each cell. So, namely, this cell has energy level 1 because it's a to the 0. This one has phi minus 1. This one has phi minus 1, etc. I'm not going to do the rest, but that's it. Any questions so far? So, for the reason that we're going to be operating with sums with a bunch of these numbers, I've written the same equation right here because we're going to use this many times. Many times? Not many times. Like a couple times. Okay, so let's get started. We'll leave that up. So, to go along with our proof sketch, We have defined our energy. Now we want to talk about what happens to the total energy, which remember we've defined to be the energy, the sum of the cells of energy on which soldiers stand. We're going to show that the total energy doesn't increase when a soldier moves. Remember, that's what we're trying to do here. We're trying to say that no matter what, we can't increase our energy. So that's what we're going to do right now. And just to make it a bit more concrete, let's say that we have a soldier here, a soldier here, a soldier here, and a soldier here. So this is a to the 6th, a to the 7th, a to the 7th, and a to the 8th. And this is an initial configuration. Notice that everyone is below the horizon. So I could say that I'm going to start with this board and try to get to the 5th floor. Who can tell me what the total energy of this initial configuration is? Where this is a to the 6th, this is a to the 7th, a to the 7th, and a to the 8th. You don't need to tell me like the number, but sort of an expression. Yeah.
A to the 6 plus 2, a to the 7 plus a to the 8.
Exactly. Good. So just to repeat them, we said a to the 6 plus a to the 7 plus a to the 7 plus a to the 8. It's just the sum of the energies of the soldiers. Okay? So, on to the next step. I'm going to prove that any jump doesn't change the total energy. I mean, doesn't increase the total energy. Oh, whoops. Please don't work. Oh, wait, no, I'll do this. Love this. Okay. So first let's talk about a vertical jump up. Okay? So we only really need to consider 3 cells. Make it pretty big. Wherein we have one cell below another cell jumps to become this configuration. Okay? So let's talk about what happens to the energy that we've defined at that point. So because if you look at any column, the exponents go in ascending order, the energy of this configuration will be a to the d. Will be a to the some exponent d plus a to the d minus 1 goes to a to the d minus 2. So in theory, I could say 0 plus this plus 0 plus 0. Okay? How am I doing so far? Does this make sense? Okay. We started with this energy and we go on to this energy. Now remember, what did I say was A? A is the solution to this equation. So remember, I want that this is bigger than or equal to this. So right now I'm going to test that. Because I want this energy to be higher than this. I don't want the energy to go up. So if I factor in a to the d minus 2, actually I'm going to divide both sides by a to the d minus 2. That will give me a squared plus a is greater than or equal to question mark 1. So I just divided both sides by a to the d minus 2. Okay? Is that okay? We know we didn't divide by 0 because a is not 0. And then, I mean, if we just look at this equation, which is what a is, and add an a to both sides, we realize that a squared plus a is 1. The golden ratio squared plus the golden ratio is 1. That's actually pretty interesting. I mean, just in terms of if you think about what the golden ratio actually is. It's the only number whose property is that its square plus itself is 1. And so this is satisfied. right? A squared plus A is 1, so it's greater than or equal to 1 for sure. All that we're saying is that if we perform a vertical jump up, our energy level stays exactly the same. The energy level of this triplet is 1, and the energy level of this triplet is 1, or proportional to 1. I'm slowing because I see a lot of writing, but does anyone have any questions at this point? Making great time, so definitely feel free, yeah.
Why is it important that it maintains the same energy or has more energy?
Sorry, why is it important that?
Why is it important that have to maintain the same amount of energy or have more energy when it's transferring?
Good question. So it's important that the energy is either maintained or after a move it goes down, because the proof relies on the fact that the total energy of a start position, like every soldier below, the total energy of that position is necessarily less than the energy of one cell on the 5th level. So if we prove that any move only serves to decrease the energy, and that the energy starts lower than the energy here, then there's simply no way that our total energy could approach 1. It would continually go down with jumps. With vertical jumps, it would stay the same, but with any other jump, it would go down. And I can assure you, you're not going to get to that cell by vertical jumps. But in any event, it doesn't matter because you would need, yeah. Yeah, so good question. Any other questions? Okay, good. So, in a similar fashion, I mean, this may seem silly, but let's talk about vertically jumping down. So again, if we look at how we've defined the energy levels, they are increasing as we go down. So this will be something like A to the D, where D is just some number depending on where we are on that board, plus A to the D plus 1, and it will transition into A to the D plus 2 after a jump. Okay? So we're just going to do a pretty similar thing as we did before. So we ask the question, is the initial configuration greater than or equal to the final configuration? Well, if we divide both sides by A to the D, we get 1 plus A is greater than or equal to, question mark? A squared. Okay? Does anyone have an idea as to how we could show that this inequality is true? I'll write it up here so you can see. I do admit, we are using a bit of trickery to show that these inequalities are true. But in fact, you'll notice that all of them are utilizing these fundamental equations of the golden ratio. So the trick in this case is to realize that A squared is just 1 minus A. So if we substitute that in, we ask whether 1 plus A is greater than or equal to 1 minus A. And indeed it is. I mean, for sure. A is a positive number. Adding something to 1 is greater than subtracting from 1. So what we've shown thus far with our moves analysis is that up and down do not increase the total energy. The energy before an up move is the same as the energy after. So in fact, if we wanted to talk about a horizontal move left, for example, A to the 7th plus A to the 8th becomes A to the 9th. Well, we're sort of repeating ourselves. We've already proved over there that if we add A to the D plus A to the D plus 1, it is greater than or equal to 8 of p equals 2. So we're not going to be too repetitive. We're only going to talk about the one case we haven't talked about yet, which is a horizontal jump, like at this meridian. And the reason we've talked about every other case. I mean, if you wanted to do a to the 7th, a to the 8th, a to the 9th, we've already talked about that in the vertical jumps. We have not talked about what happens if you have something like a to the 6th jumps over a to the 5, and the total energy afterwards becomes a to the 6th. So just to write that algebraically. If we talk about going from a configuration like this to this, where this one jumps over this one and becomes this one. The reason we never talked about that with the vertical case is because this is kind of special, right? In vertical, it's certainly ascending all the way down, but in horizontal, it goes 8, 7, 6, 5, 6, 7, 8. To draw the analogy again of the Manhattan metric, it's like if you're walking down West 4th and you start at the East River, your distance to Union Square decreases, but then as you pass, I think as you pass like one of these roads, your distance will increase again as you get to the Hudson. And I mean, that's actually true of any metric road. But anyway, so let's talk about this case, and then that'll be it for the moves. We'll prove that every move goes either down or stays the same. So the question we have to ask is to repeat myself, whether this sum, which is the energy of this configuration, is greater than or equal to the energy of that one. So applying the same technique, we get a plus 1 greater than or equal to question mark a. Did I do that right? No, I didn't. Right, so applying the same technique, we divide both sides by a to the d. We get a plus 1 greater than or equal to question mark a. No, I did this, right? Yeah. And this is certainly correct. Okay? So that actually is all the cases that we have to worry about with the moves. Any jump from here over here to here, horizontal, vertical, what have you, we've addressed it. It's one of these exponent transitions. And so what we've proven is with this metric, which you'll notice we've really critically used the fact that we're working with the golden ratio, which satisfies this equation. With this metric, any jump will take the total energy of the initial configuration and either decrease it or keep it the same. Okay? Okay. So prove no soldier jump increases the total energy. Good. Any questions? Okay. So now, finally, we will end the proof. We will end the proof by showing that any configuration of soldiers below the horizon necessarily has total energy less than 1. So I will do that right here. Okay. So what I'm going to do is I'm going to say, okay, I want to show that any initial configuration has total energy less than 1. Well, I mean, a priori, what's the naive way to look at this problem? Why don't we just put soldiers on every block south of the horizon? Like, first of all, that will give us the most energy, for sure, right? We want as many of these cells occupied as possible. And second, I mean, if we have an infinite checkerboard, we might as well fill the bottom half. But in fact, even that will be insufficient. And that's the thing. I mean, any initial configuration is worse in terms of energy than that, and even that is less in terms of energy than just one soldier on the target cell. And so to show that that's the case, we'll calculate the sum of the total energy of the bottom half being filled with soldiers. So this is where geometric series comes in. So to do that, I'm going to say, okay, well, let's first, I mean, there's sort of a symmetry going on. So the first thing I want to do is calculate the sum of this column's energies. So that's just a to the 5th, plus a to the 6th, plus a to the 7th, plus a to the 8th, plus a to the 9th, dot, dot, dot. Okay? We're just calculating the energy of if every cell in this column are filled by a fully. And so this sum, I mean, this is a geometric series. We could factor out a to the 5th, so that this becomes 1, plus a squared, plus a to the 3rd. Do you agree with me that this is the same thing? Yeah. And then this is this. Right? This is the sum of all the powers of F. So this just becomes a to the 5th times 1 over 1 minus I. By that formula over there. Now from here until the end of the proof, which will be probably about, to the end of the calculation, which is the end of the proof, there's going to be so much trickery. This is really where the golden ratio comes in and just solves everything for us. Because we want to make this look pretty simple. This is a to the 5th times 1 over 1 minus a. But remember, because we're working with the golden ratio, 1 minus a is just a squared. So this just becomes a to the 5th times 1 over a squared, which is a cubed. And for the rest of this calculation, we're just going to do a repeated version of this. So if these 4 lines are what I want to be sure that everyone understands before everyone. So if there are any questions. This is a pretty standard way of finding the solution to a geometric series, with the addition of the golden ratio trick in the bottom. Okay, so let's see. You know what? Oh, here we go. Okay, well, I'm going to say the. I'm trying to break that board line. Okay, so a cubed is the sum of all the energies of this column. So now I want to ask the question, well, okay, I'm going to write a cubed up here, so we remember it. Well, that's good. What about the sum of the energies in this column? So that's just going to be a to the 6th, plus a to the 7th, plus a to the 8th, plus a to the 9th, etc. Now, this is kind of a challenge question. Can anyone tell me, based on what we just found from this column, that the sum of those energies is a cubed? Immediately, what the sum of these energies is? Yeah. A to the 4th, exactly. Nice job. So we could just do the same thing we did with this, where we get this geometric series and we get this form and then we reduce it. But in fact, we've already done work, so why don't we reduce the amount of work we're doing? And factor out an a from this form to get this. But this we already solved. So this is just a times a cubed. Okay? So now we're pretty much set to tackle the actual question, which is the sum of the total energy of soldiers on every cell in the bottom half. Because look, I mean, if I write for each column, I mean, based on what we're doing over there, we know that the sum of this column is a cubed. The sum of these columns are a to the fourth. Some of these columns are a to the fifth. Then all we need to do is sum this series. Right? So I'm going to write this very explicitly. We want the sum of all the columns, sums of the energies. So we know that the middle column has the total energy A cubed. We know that the column to its right and to its left have the same total energy, which is 2A to the fourth. We know that the columns on the right of that one and the left of that one have A to the fifth. We'll just keep repeating the same strategy that we've done. And we'll get a series that looks like this, where the exponent is allowed to go to infinity. So, I mean, this is just a geometric series. We have a formula to work with this. So, well, how do we want to do this? I mean, the rest of these are going to have 2's, so I'm going to work with those individually. I'm going to leave the A cubed here, and I'm going to factor out a 2. So this becomes A to the fourth, this A to the fifth, this A to the sixth. Okay? That move was good. I just factored out a 2. I'm going to go one step further and apply my standard technique, which I've been doing for other sums that look like this, which is factor out the first term. So if we factor out an A to the fourth, we get A cubed plus 2 with, yeah, okay, 2A to the fourth plus 1 plus A squared plus dot dot dot. So was this move okay? I just factored out an A to the fourth. And then I can write that sum as A cubed plus 2A to the fourth, 1 over 1 minus A, because of that formula. I mean, the goal when we look at something that's just a bunch of ascending powers is to factor whatever elements out that we need to get it looking something like that. Because then we can substitute something that's not a freaking infinite sum. Something that we can actually do some algebra on. Now again, using the trick of the group ratio, I plug in A squared for 1 minus A, and this becomes A cubed plus 2 times A to the fourth over A squared. Okay. Almost there. I'm going to get rid of my formula. I'm not going to get rid of it. Yeah, I'll work it. So I'm still attempting to simplify this expression, which remember is the sum of all the energy in the bottom half. So I'm going to rewrite it right here. A cubed plus 2 times A to the fourth over A squared is just A squared. Applying a bit more trickery. This is the level in the proof when the reader is something like, I understand what's going on, but if you ask me to come up with this myself, there's no way. We're going to change this into A squared times A. And then we're going to substitute in 1 minus A for A squared. And then a smidgen about, this is probably getting too small for people to back to see. I'm going to take this expression and move it up here. So I'm rewriting that. 1 minus a times a plus 2a squared. If I multiply out, I get a minus a squared plus 2a squared. And this is kind of slippery slope of simplification. Like at the beginning we have this complicated expression and already we see it's getting simpler and simpler and simpler. This becomes a plus a squared. Minus a squared plus 2a squared is plus a squared. And finally, because of this equation, which describes the golden ratio, we know that a squared plus a is 1. So what did we just do? We calculated sum of each column, if there were soldiers on every column, for their energy. We got a cubed for the middle one, a fourth for the ones on its side, a fifth for the ones on those sides. And then we summed up the columns, which was originally written here, simplified here, to get the total energy of every cell in the bottom half being occupied by soldiers. And in fact, that total energy is 1. So what does this mean? This means that if we put soldiers on every cell in the bottom half of the Conway soldier checkerboard, the total energy would be 1. Similarly, if there were only one soldier on one cell in the 5th level, its energy would be 1. But we know that jumps either decrease or maintain the same energy. So if we start with a finite number of soldiers, there's simply no way we can do it. It's mathematically impossible. When someone says mathematically impossible, this is why we use math to demonstrate the answer. So any questions about that? Okay, well, yeah, since we didn't have questions, I guess, yeah, I kind of got through everything I wanted to talk about. So if you guys, I guess we can, yeah, do you have a question?
I mean, I missed something, but why doesn't this prove that you can't do 4 or row 4?
Well, the total energy of
doesn't work for row.
Sorry? I was going to say, well, first of all, a solution to get to the 4th row has been demonstrated, but the reason that this proof doesn't show that is because if you had a soldier on a cell in the 4th row, then its energy level, I mean, by this definition of energy, its energy level would be A. I mean, without loss of generality, it would be A or something smaller than A. And in fact, it is possible for us to have a number of soldiers below the horizon with total energy greater than A. So in theory, we can lose a bit of energy as we're moving up, but so long as we keep an energy above A, yeah, we can do it. Like we might, like the solution, all right, so you remember I said that the solution is, I mean, the minimum number is 20. If we applied this metric of energy to the solution for 20, we might have that the final solution, like the one soldier on one cell has energy A, and the 20 soldiers in their positions has energy A plus like 0.3 or something like that, A plus some number, which is shed energy-wise as we do horizontal moves. So I'm going to say that's it. I don't really have anything to talk about for the next 10 minutes, so feel free to do as you may. But I'll stay after for questions and stuff like that. Yeah, did you have one more question?
Well, no, my point was like, why can't we just shift the entire thing down so that 4, like 4 in the middle would equal 1 and everything else?
That's a tremendous question.
That's the question.
So if we did that, then our horizon would be this line, right? Like if we shifted it.
Yeah.
So our horizon would be this line, right? But then we can have a total energy below the horizon, which is still greater than 1, because we'll have these elements as well. So if we put soldiers on every position below the horizon currently, we've already calculated that we would have total energy of 1. But if we did it with the horizon moved up 1, we'd have 1 plus whatever the sum of all the energies in this row is. So we can shed some energy. Yeah, this is really something, because if you look at the solutions, if you look at what the initial configuration should be for 1, 2, 3, and 4, they all look pretty similar. It's like 2 soldiers here, and then, okay, 2 soldiers here, 2 soldiers here. And then for the next one, it's similar shape. And the same strategy seems to be applied, but as soon as you hit the number 5, that's it, game over. It's like there's some fundamental quality of how we fit the pieces in the board. It seems like there should be some geometric intuition as to what is limiting us here. But we don't really have a good idea of what that is. So I guess, yeah. And yeah.
If the board is infinite, why does it matter where the horizon is? Since we have an unlimited amount of spaces.
So the definition of the game is that we have an infinite checkerboard and a horizon. And the goal is to get 5 above the horizon, right? So it doesn't matter where the horizon is initially put, but once we've picked where it is, we define energy this way, and we achieve our goal. If we looked at, like, if you're suggesting that instead of this, we used, like, this as the horizon, like this line instead, then you're right that the total energy wouldn't sum the way it has before. But all we'd be saying is that we can reach this cell, which we already knew because that's only 4 above the horizon. Yeah, our goal is related to the horizon, so that's why it sort of matters where it is. I guess one more interesting thing is that, so we worked in dimension 2 here. This is a 2-dimensional plane. This result actually generalizes. If we say we're in the n dimension, then 3n minus 1 level 3n minus 1 can't be reached. I mean, you can plug in here. For example, in this case, 3n minus 1. Well, we're in the 2nd dimension, so 3 times 2 minus 1 is 5. The 5th row can't be reached. If we were playing Conway soldiers in some 3-dimensional space, is there any game that's like that, like Cubert or something like that? Or... Well, anyway, if we had 3-dimensional cells and we had some plane that acted as the horizon above which the soldiers would try to jump, then they could only get up to 8, because 3 times 3 minus 1 is 8. I'm sorry, they couldn't get to 8. Yeah. And in fact, John Conway when he gave this proof, he published it, it was a general proof. He didn't count rows and columns like he did. He talked about hyperplanes. He talked about a general n-dimensional column, so to speak, or an n-dimensional plane. And in that proof as well, the energy definition is exactly the same. We use the Manhattan metric, and the base of the exponent is the golden ratio. Well, okay, yeah, thank you for coming to my talk. My email is right there if you want to, any questions about this or resources or ask about college and stuff like that. And I'll also be here afterwards if you have any questions about that as well. So yeah, thank you.